Great Mysteries of Physics is a series supported by FQXI, the Foundational Questions Institute, a think tank and funding agency that explores the foundations and boundaries of science. Find out more at fqxi.org.
Welcome back to Great Mysteries of Physics from The Conversation. I'm Miriam Frankel, and I'm your host for the series. Imagine standing before a firing squad with 50 gunmen aiming rifles at you. Clearly, this is your last moment. But somehow, the bullets all miss and you survive. This could simply be an extremely lucky coincidence. The squad would be statistically likely to miss a couple of times if you reran the event over and over. But wouldn't you feel perplexed about your survival? Wouldn't you want to seek answers about how it could have happened? This metaphor was put forward by the philosopher John Leslie to demonstrate how the existence of life in the universe also relies on enormously improbable conditions. Values of forces and particles seem to line up perfectly to enable the evolution of intelligent life. Indeed, this conundrum popped up in the first episode of the series when we discussed whether time is an illusion. It suggested that the arrow of time, which propels us from the past to the future, is down to increasing entropy, which is a measure of disorder. But this must mean that the universe started out in a surprisingly low state of entropy. Why? This is a major headache for physicists, and it doesn't just relate to entropy. Constants, for example, the speed of light, are universal quantities of nature. By baking them into our physics equations, we can accurately describe what we see around us. But the physics itself doesn't require the constants to have any particular value. We have just added the numbers to match our calculations with our measurements. So why do they take the values they do? That's what we'll discuss in this episode. Importantly, are the constants somehow fine-tuned to allow life to exist? And if so, who fine-tuned them? Could a superior alien species have created our entire universe as a computer simulation for their entertainment? Paul Davies is a theoretical physicist at Arizona State University. He is an expert on cosmology, quantum theory, and astrobiology, and has spent time researching fundamental constants, a topic which he's also written several popular science books about. I started by asking him what fundamental constants are.
I think everybody knows there are laws of physics or laws of nature, and these are mathematical relationships. And one very familiar one is Newton's inverse square law of gravity. And all that says is that the sun pulls on the earth with a certain force, and if you went twice as far away, the force would be 1/4 of the force it actually experiences. So it drops off in a precise mathematical way. What that law doesn't tell you is the actual strength of the force. Just how much does the sun pull on the earth? Same thing, you drop an object, it falls to the ground because the earth's gravity pulls it. But by how much? And why not twice that or half that? And that, we say, is an undetermined constant. You just have to measure it experimentally. And you can always ask the question, well, why that number? Why didn't the universe come with gravity twice as strong or 10 times as strong? We don't know the answer.
Yeah, a lot of people probably remember from some sort of physics lesson that there's a letter G that you plug into your Newton's equations if you want to calculate a force between objects or whatever. And it's that we're talking about, isn't it? This G, for example, for gravity, you plug in a number that you've measured and suddenly you get the right answer.
Right. But the important point about this big G, that once somebody's actually measured it and you know what the number is, you look it up in a book, but that number is the same throughout the universe. So it's a universal constant. It's not like there's one big G on Earth, a different one on Mars, and another one in the Andromeda galaxy. As far as we can tell, it's a constant. So we call this a fundamental constant of nature. And there's a lot of puzzlement as to why it has the actual value that it does.
And there are loads of those, isn't it? How many have we got? How many fundamental constants are there?
Well, if you look up in a book, you'll see there's 30-something of these undetermined constants, but the word fundamental is a loaded one. We don't know whether some of those constants are linked deep down. If we had a deeper theory, we'd find that they're not actually independent of each other. And some people who dream of like a grand unified theory of everything wonder whether, in fact, if we had that theory, all of these constants would be connected in some way. There might only be one undetermined parameter at the bottom of this, and that would simply just set the scale for things. But we don't have that theory, and so at the moment we've just got all these numbers, and you just have to measure them, and then you look them up in a book.
Physicists have been suspicious about these constants for nearly a century. There's even research showing that if we change their values, life couldn't evolve.
It's a wonderful universe, but maybe it could be improved. And imagine you could play God and you had a designer machine in front of you with a lot of knobs on. You could twiddle these knobs. You twiddle this knob, you make all electrons a bit heavier, and you twiddle that knob and you make the weak nuclear force a bit weaker, and so on. And there's going to be 30-something of those knobs because those are the undetermined parameters. And what you discover, of course, you can't do the real experiment, but you can do the calculation, is that some of those knob settings really are critical for the existence of life in the universe. Twiddle a few of those knobs just by even a little bit, and it would have lethal consequences. You wreck the possibility of there being any form of life, at least any form of life based on familiar things like chemistry.
Chemistry is important because without chemistry, there would be no elements, no reactions, no life as we know it in the universe. Recent research shows that the masses of the proton and neutron, so that's the particles that make up the atomic nucleus, must be astonishingly similar and huge compared to the mass of the electron. In fact, the ratio of the mass of the electron to the mass of the proton is tiny, 1/1836. But chemistry as we know it depends on this ratio. If the electron mass weren't much smaller than the proton mass, we couldn't have stable ordered structures such as living cells. Neither could we have stable stars that lived for long enough to allow life to evolve. There's a similar balance between the force of electromagnetism and that of gravity. Because gravity is so weak in comparison to the electromagnetic force, this ratio is huge, at 10 to the power of 40. If gravity were a lot stronger, stars could have formed from less material, meaning they would be smaller and have short lifetimes. This would be troubling, as it took human life billions of years to evolve on Earth. And if gravity were significantly weaker, matter in the early universe could not have clumped together very well, meaning galaxies, stars, and planets couldn't have developed. Another mystery is why we experience only 3 dimensions of space: depth, height, and width. If we experience more dimensions, scientists have calculated that there would be changes to the gravitational force so that planets would struggle to stay in orbit around stars. And if there were fewer, well, although planetary orbits could be stable, it might be unlikely that complex life could evolve. Just think about the DNA double helix, for example. It is 3-dimensional. Another famous example of a fine-tuned parameter is to do with the production of carbon, which is the basis of life on Earth.
There was one that was much discussed way back in the 1950s due to Fred Hoyle, the British cosmologist, gave me my first job. And he noticed that carbon, which is the critical life-giving element, its formation inside stars was a close-run thing. And that's because it depends very sensitively upon the values of some of these constants, in particular because you can make carbon in stars only by having 3 helium nuclei coming together and colliding at once. And that's a very improbable affair if it wasn't for a certain quantum mechanical property that greatly amplifies that process. And so he noted that if the nuclear force were just a little bit greater or less, that it would go off resonance, it would go off this critical amplifying factor. The way he put it was, it's as if a super intellect has been monkeying with the laws of physics.
While this is all fascinating stuff, some physicists are very uncomfortable with a fine-tuning argument. They question what the point is of pondering what would happen if a parameter changed a little in value, when we don't actually have a theory which says what that parameter should be in the first place. So how can we actually know whether they are unusual?
But there is an exception to this. The accelerating expansion of the universe, which is thought to be caused by a so-called dark energy and is related to a constant, often referred to as the cosmological constant.
So this was described by Stephen Hawking as the greatest failure of theoretical physics in history. And let me just explain that we now believe that the universe is not just expanding, but is accelerating in its rate of expansion, and that the term that we give to the causative factor is dark energy. But if you ask what that is, it's just the energy of empty space. And you might think, well, why should empty space have any energy? Because it's empty. And my answer is usually, well, why not? But actually, there is a good reason. Quantum mechanics tells us even empty space is not totally empty. It's full of a seething ferment of activity where particles pop into existence and go away again. And you can work out the energy of that. And I did lots of these calculations myself a few decades ago. And you can say, well, let's see if we can work out what is the energy of empty space in an expanding universe like the one we see. And the number you come up with is about 120 powers of 10, bigger than what the astronomers measure. And so this is all a bit of a disaster, and it's often called the dark energy problem. And there are all sorts of hand-wavy possible solutions, but no agreed solution.
Fred Adams from the University of Michigan in the US has done a lot of research on just how fine-tuned the universe really is. And he has discovered that the universe may be a bit more robust than physicists have so far given it credit for. I started by asking him how we actually know whether the universe is fine-tuned for life at all.
Yeah, well, that's the essence of the problem, is that if all the constants had to have lucky values, then it would be unlikely that we would be in this situation. But the key thing before you ask that question is to ask the more fundamental question: what range of these parameters actually allow for stars and the universe to live a long time and for life?
Right. So physicists have done all sorts of calculations based on, what happens if we change this parameter a little? If the gravitational force is a lot stronger or weaker, will that affect how matter can clump together to create planets and people and so forth? But you're saying that, well, you have to look in detail at how stars actually work and these mechanisms and try to change the value in a complex simulation to find out what really would happen.
Basically, you have to do the calculation. If you want to say whether or not stars work, you have to solve the stellar structure equations. So that is exactly what I've been trying to do.
Stars are of key importance when it comes to fine-tuning, because they've ultimately created all the carbon and other elements that life is made of. Without stars, there'd be no pleasantly warm planets or moons for life to evolve on.
And their ability to support life seems precarious. Previous research suggests that if the strong force, which binds together the atomic nucleus, were just 2 to 4% stronger, protons would bind together, which would speed up nuclear reactions in stars.
This would make them run out of fuel before life had a chance to develop on surrounding planets. But Fred isn't too worried.
Well, what I found in a nutshell is that the range of the parameters that we're talking about are wider than what people often say. So you can change the value of electromagnetism, the fine structure constant, by a factor of about 100 up and about a factor of 100 down, and still have working stars. You can change the value of gravity, the gravitational constant, almost 1,000,000 times stronger and 1,000,000,000 times weaker, and still have stars. So these ranges are larger than what people have talked about before. And I think the reason is that they hadn't solved the stellar structure equations.
Okay, so they had just kind of looked at the overall numbers, sort of back of an envelope calculations.
Or not even that. They just sort of said, well, it must be sensitive.
So how much had people before your work, how much did physicists who looked into this expect that something like the fine structure constant or the gravitational constants, the two examples that you used, could change? You mentioned a factor of 100 up or down, or 1,000,000 and 1,000,000,000 for the gravitational constant. How much more than we thought is that?
There was a general feeling that the ranges were small. And all I'm saying is that we should calculate the ranges. And when you do the calculation, the general result is that the ranges are usually a couple orders of magnitude. Sometimes bigger, sometimes a little smaller, but most of the time when you look at the allowed parameter space, it can vary by at least a couple orders of magnitude. That's a couple factors of 10, to be clear.
Which parameters are the most fine-tuned?
That depends on how you do the accounting and what you care about. But the way I would answer your question is to slightly rephrase it and say, what's the aspect of our universe with constants of nature that is most easily changed to make the universe very, very different? Maybe kill the universe or make it so it doesn't support life. And I think the answer is this. It'll take a minute to explain. In our universe, a neutron decays to a proton, an electron, and an antineutrino.
Okay, so neutrons are particles that make up the nucleus alongside with protons.
That's correct. Now, just hold that thought and then consider the hydrogen atom. A hydrogen atom is an electron orbiting a proton. If it were energetically favorable, the electron could combine with the proton and form a neutron, thereby killing the hydrogen atom. And if you don't have hydrogen atoms, you don't have water, and you would have a very different universe. So that is the closest our universe is to a failure point, to have hydrogen atoms become unstable and spontaneously turn themselves into neutrons. The reason why that doesn't happen in our universe is that the electron doesn't have enough mass to actually make a neutron by combining with the proton. The mass difference between the neutron and the proton is big enough that that doesn't happen. But if you crank down that difference by changing the mass of the quarks, which are the fundamental constituents of the protons and neutrons, then you could actually make the hydrogen atom unstable.
So quarks are the fundamental building blocks of matter. There are actually 6 different types of quarks, but the matter that we see around us is mainly made up of 2 quarks called up quarks and down quarks, which create protons and neutrons. So the mass of a proton or a neutron depends on the mass of the quarks that constitute it. And it turns out that one of the quarks, the down quark, is actually very fine-tuned.
The up quark can change upward by a little bit and downward by quite a bit, but the down quark mass can only vary by about a factor of 7.
But how do we determine whether a factor of 7 is fine-tuned or not?
Well, it depends on how you call fine-tuning. If you want to tune a radio, you have to know the frequency of the signal to 1%. And 1% is much more tuned than a factor of 7. So it's much harder to tune a radio than to tune a universe.
A lot of previous research has looked at what happens if you change one parameter by 1% or 2% or whatever it is. But you've actually said, well, what if you change several parameters at the same time, several constants? So you change gravity, but you also change the electromagnetic force, and you also change the expansion rate of the universe and so forth. What happens when you do that? What was it you found?
Well, that opens up more possibilities for a working universe. One good example of that is something called the cosmological constant, or the amount of vacuum energy in our universe. It's also called dark energy. So people have claimed that if you were to have a universe with a larger value of that cosmological constant, then the universe would accelerate earlier and it would be harder to make galaxies. So you can't make that constant too much larger and still have a working universe because we wouldn't form galaxies.
Because all the matter would be pulled apart. Is that what would happen?
Right. So early on, the universe is not accelerating and structure can grow. But later on, when the cosmological constant takes over, it starts accelerating things apart and it makes it harder for things to grow, or more precisely, growth freezes. And then you don't have any more growth. So if that accelerating freezing out happens earlier, then you have less structure in the universe. And if you turn that knob too far, you don't have any structure in the universe. You don't have galaxies, and we're not here. So you can only go, depending on how you do the calculation, factors of 10. One person got 240. You can only make the cosmological constant larger by that factor and still have a working universe with structure. However, if you vary another parameter, namely the amplitude of the density fluctuations, which basically sets the initial density contrast of the universe when structure starts, if you make that larger, then you can make the cosmological constant enormously larger. And here's the way it works. In our universe, that structure formation starting point, that parameter is 10 to the minus 5, which is kind of unnaturally small. But imagine that it's 10 to the minus 4 instead. Well, then you can make the cosmological constant 1,000 times larger and get back to the same kind of universe. If you make that amplitude 10 to the minus 3, then you can make the cosmological constant 1,000,000 times larger and still have structure formation the way we do.
So, as Paul Davies explained earlier, the cosmological constant, which represents dark energy, must be very small, and much smaller than theory suggests. But according to Fred Adams' calculations, if the size of density fluctuations in the early universe were 10 times larger, dark energy could be a lot bigger and still allow for life to develop. This begs the question, could the universe be optimized for life even more than it currently is?
There's this tendency that we think that the laws of physics are actually optimized for life. And the fine-tuning arguments that we're starting this discussion with sort of suggest that our universe is the best it can be for life, and why is that? But I think it's an interesting question to ask, well, can you actually design a universe that has better constants of nature, that's more friendly to life? And I think you can. You can make a more logical universe that produces more structure, potentially produces more habitable environments, and I guess by implication supports life better.
You're listening to Great Mysteries of Physics from The Conversation. Fred's work makes an astonishing point. Not only may the universe not be as fine-tuned as we thought it was, but it may not be as life-friendly as we thought it was. Perhaps, if the constants had other values, we'd have more life in the universe. Here's what Paul thinks.
There are very different circumstances, different pathways to life. But if each of these is relatively isolated in the parameter space, it still looks like there is something to be explained. If you imagine being like the creator, you stick in a pin, you've got this multi-dimensional parameter space. And I've mentioned 30-something, maybe less when we get a fundamental theory, but nevertheless, there'll be these parameters and you stick in a pin at random. What are the chances you'll hit one of these blobs that leads to life? And I think that answer is very low probability.
Regardless of how fine-tuned the universe really is, it does beg the question of why it is that way. Why do the constants take the values they do? Perhaps the answer is hidden in some ultimate theory of reality that is yet to be discovered.
There's a three-way split on this topic. On the one hand, you've got people who say, oh, we live in this universe that's cooked up for life, it's fine-tuned, it looks like it's rigged in favor of life, this is evidence of some cosmic designer, so that's a sort of religious view. And then that's anathema to most scientists. So then there's a group of scientists who say, no, this has an easy explanation, that we're making the mistake of assuming that there's just one universe, but if there's a vast multiplicity of universes and they each come with different values of these fundamental constants, just like sort of rolls of the cosmic dice, and it's all random, that here and there, just by chance, you'll get all the right numbers, and then beings will pop up and marvel at the fact that they live in a universe that looks like it's rigged in favor of their existence. But actually, we're just winners in a cosmic lottery. And the vast, vast number of universes simply go unseen and unlamented. The numbers didn't come out right. So that appeals to some people. But then there's another group of physicists who say, oh, this is horrible, because what we want to do is to explain what these fundamental constants are in terms of some deeper theory, string theory or something of that sort. And although we don't have that at the moment, we shouldn't give up. And that if we work hard enough, we will see that these are not just haphazard numbers, but they will be nailed down by theory. And then they will be what they will be. And the fact that they're consistent with life is a bonus or an irrelevant thing or something we've imbued with greater significance than we should. The reason that we're fixated on the universe being in favor of life is because we're living beings. So, we would say that. So it's a sort of egocentric thing.
This idea that the universe is one of many in what's called a multiverse is becoming increasingly popular, not least because it solves the problem of fine-tuning. Here's Fred.
If you allow for the possibility of other universes, then you allow for the possibility that the constants of nature, the strength of gravity and so forth, are different in those different regions. So then we have the question, why does our region give us constants that allow us to be here? Now, there's a couple different answers to that. One is that with this vast collection of different universes, the universes will sample all the different combinations, so we just happen to be in the one that we're in. Moreover, you can take that one step further and say, well, we're here. So the fact that we're here means we have to be in the universe that allows for structure and life to exist. Otherwise, we wouldn't be here to ask the question. If you could start from the basics of string theory or M theory or its descendants and prove that there was only one way to construct a universe that's mathematically consistent, and it was ours with our values of the constants, and you could calculate all of the values of the constants from first principles, then you would be done.
So can we dismiss concerns about fine-tuning without a fundamental theory by just assuming there is a multiverse? Paul doesn't think so.
I think there's a very good argument for a multiverse, and it's the following, that we all think that the universe began with a Big Bang, and either the Big Bang was a supernatural event or it was a natural event. And I'm a scientist, so I believe it was a natural event. But if a natural event can happen once, it can surely happen again and again and again. And so that leads to the idea of many bangs scattered throughout space and time. And then a sort of grandiose view, you take a sort of proverbial God's eye view of this lot. What you've got is like a multiverse of bubble universes in some expanding sort of superstructure. And if each one comes with its own set of laws and its own set of fundamental constants, then by this sort of lottery argument, it's inevitable that some of these will eventually give rise to life. However, people then leap to a conclusion that I think is not justified, which is that there's nothing left to explain. Everything about the world is accommodated in this sort of cosmic lottery scheme, but not a bit of it, because in the multiverse, you still need laws and you still need special conditions and a whole lot of constraints. So you haven't explained everything at all. You've just pushed the problem up a level. So I usually say 2 cheers for the multiverse, because I think it's better than just saying God did it. On the other hand, that doesn't mean we've explained everything.
Yeah. So who created the multiverse?
Right. And is the multiverse eternal, or did it have an ultimate beginning? And if so, we're right back with the same problem.
Yeah, why were the conditions such that that particular structure would evolve that then gave rise to life?
Right. So even if you go to this multiverse of many universes, and the many universes can have lots of different variety, we still have to have some sort of law-like organized arrangement in the multiverse. How did that come to exist? And if it has always existed, well, that doesn't explain why it is as it is and not like something else. So I'm always fascinated by ultimate explanations of things.
You said 2 cheers for the multiverse before. So what gets 3 cheers?
I just mentioned it. If we finally did have a complete explanation for existence, that is, why is there a multiverse? Why does it have the form that it does and the laws and principles that it does? Is all that explained in terms of something deeper that we would find totally satisfactory? Then we would probably say, that's it. We have really explained everything. But the problem I see is that we are products of biological evolution, that we have evolved to survive in the proverbial jungle. We haven't really evolved our brains to solve the ultimate problems of the cosmos. And it's truly amazing that using science and mathematics, we have got so far. But there's no guarantee that our cognitive abilities carry with them the secret of existence in this ultimate sense. And I often toy with the idea that if we develop artificial intelligence of sufficient power, that we let AI loose on these sorts of issues, after 1,000 years of cogitation, the AI might say, yes, it's all clear. And we'd say, well, do tell us. And the explanation would be completely meaningless. It would be outside the scope of human beings, in the same way if you tried to tell your dog about quantum mechanics. It's just not going to get it.
No. What about the idea, though, that, as you said, if we're in a multiverse and there might be some universes in that multiverse that are better suited to intelligent life than our own, maybe with more intelligent creatures, could it be that we haven't been created by a god, but by an alien civilization that created a big bang in their lab and created our universe, or maybe just put us in a simulation or something? Wouldn't that kind of also be an explanation.
Absolutely, yes. So I love this idea, although it's hard to know how seriously to take it. It's true that as our technology develops, if we don't blow ourselves up, we can imagine a time in the far future when we will understand the laws of physics well enough that we can reenact the conditions that led to the Big Bang. It may not actually require huge resources, because one of the oddities about the universe, if you tot up what is the total energy of the universe, it's actually very close to zero. So it may be that we could create a Big Bang in the lab, so to speak, without having to have vast resources. And then we would create a bubble universe. And that might sound alarming. You might think, well, it would engulf our own universe, eat it up. But in most of the models, it doesn't do that. It just looks like a little black hole. And you could imagine if you got sick of this universe, you could decamp to this new baby universe, which would then balloon out and expand and become, a cosmos in its own right. And if we had the ability to jump into this little bubble and get through the wormhole connecting our universe to this new one, I often like to say this is emigration with a vengeance. It's not just getting out from where you live, but from abandoning the entire universe to its fate and going to one with better prospects. So all this is very entertaining, but inevitably it leads to the thought, well, if our universe is cooked up so well for life, maybe it was manufactured by a super civilization in a preceding phase. And maybe our bubble is precisely the product of this technology, because after all, if we made our own bubble universe, we want to make sure it was consistent with life before we climbed into it. And so you can go on like that. And then you have to think, well, is this just a science fiction version of the good old-fashioned God of the Bible who made the universe in a propitious way in order for it to be inhabited by beings like ourselves? So it's the same sort of idea.
It seems the more likely if there is a multiverse with loads and loads of universes than if there isn't.
The problem about a single universe is that we think it can't be infinitely old, because it would have run down by now, run out of steam. But if it's of a finite age, if time itself began with the Big Bang, which was the prevailing view when I was a student, the origin of the universe was the origin of time and space, then under those circumstances, the formation of the universe from nothing becomes a bit of a mystery.
Whether you choose string theory or the multiverse to explain the fine-tuning of the universe, you're still stuck in the theoretical realm. And we currently have got no experimental support to prove that either theory is correct. But if we could verify them, that would obviously help to solve the problem. In the meantime, there are ways that experiments could help shed light on the conundrum.
For example, researchers are measuring the constants themselves to see if they really are constant.
So we've been using this word constants of nature, but how constant is constant? We can only ever put a finite limit. We started out talking about the constant big G, the Newton's gravitational constants. That actually is not known very precisely. It's a really difficult thing to measure. And it could well be that in the future, when we measure it more accurately, we will find it actually varies either from place to place or from time to time. Some other constants we can measure very well, like the charge on the electron and its magnetic moment. These can be measured to like 12 or 13 significant figures. But we could again imagine in the future that we might see that there are some glitches. There's some weak evidence. I don't take it very seriously, but my friend John Webb, now at the University of Cambridge, claims that there is evidence that basically the charge on the electron, it's called the fine structure constant, is slightly different across the sky. That if you look out in the universe, look over there, it's slightly different from what it is over there. Only a tiny, tiny amount, and that might indicate that what we thought was a fundamental constant is actually varying cosmically, either over space or time. And that could be true of other constants as well.
And if that were to be the case, that these so-called constants are varying over space or time, that would be a huge blow, wouldn't it, for this argument that, the universe must be fine-tuned for life, wouldn't it?
Well, it would have a curious consequence, I think, because if these constants are really variables, then it would go into the melting pot along with all the other variables that we have in the laws of physics. And so we would then demand that there is some sort of law, because it would be unlikely these variations would be random, although that in itself would be interesting. So if there was a systematic variation, you would want to have a sort of super law underpinning the laws that would capture that. And then, of course, the whole argument would start up again because people would say, but that super law, has just got the right features so that there has been a window of opportunity in this universe where the numbers came out right, at least for an epoch of which life could form. And so the fundamental argument wouldn't go away, but it would just be conducted at a deeper level of investigation.
While there is currently no reliable evidence suggesting that the constants of nature do vary, this may change over the coming decade. The Espresso Observatory at the Very Large Telescope in Chile, for example, is currently trying to measure whether the fine structure constant really does vary. Similarly, there have been hints that dark energy is growing. There are many experiments which could get to the bottom of this in the next few years, including the DESI experiment, which is installed in the Mayall telescope in Arizona in the US. In particle physics, both the Muon G2 experiment in the US and the Large Hadron Collider in CERN in Switzerland have found strange anomalies suggesting that there are particles out there that we haven't yet discovered, particles that may be linked to an unknown fifth force of nature. So that's in addition to the ones that we already know, electromagnetism, two nuclear forces, and gravity. And if that turns out to be true, we might have to rethink what we know about the strength and sizes of the forces and masses in the cosmos, including whether they are fine-tuned. So, given all these gaps in knowledge, perhaps we're just too eager to investigate whether the universe is fine-tuned. Is there any point in debating it at all? Fred thinks so.
The reason why it is, I think, an interesting question is not just for answering the question of what happens in other universes or what's the probability of getting our universe, but it also, I think, gives us a certain deeper level of understanding of our universe. And here's why. Suppose you want to test your car. What you do is you take it out on the highway. You go from 0 to highway speed as fast as possible. You take it around a curve as fast as possible. In an ideal case, you would drive it until it breaks to see how safe it really is, right? Same with an airplane. That's what test pilots do.
Yeah.
So in some sense, we want to do that with our laws of physics. We want to take these equations of stellar structure and ask, well, how much can I vary G, the gravitational constant, and alpha, the fine structure constant, and the nuclear reaction networks? How much can I vary them before the star doesn't work anymore? Now, the reason to do that is, one, to see the ranges that allow for a working star, but more fundamentally, it tells you how stars work.
Right. Okay. So we can learn other things.
That's a way to tell that we're on the right track. But we don't need to make a stellar model of the sun to get the sun's luminosity. We can just measure that. The reason to get the stellar model to calculate the stellar luminosity is to understand what's going on inside the sun. So by doing these kinds of calculations where we take the stellar structure equations and the cosmological equations to their breaking point, we get a certain understanding of how the astrophysical structures in our universe work. And that's fundamentally our job as astrophysicists and physicists, is to understand how the universe works.
And to break stars.
And to break them.
It may indeed be natural for our inquisitive minds to ask why our universe happened to be able to accommodate intelligent life like ours, creatures who sit around debating why we're here at all. As Paul Davies has argued, it is true that the fundamental constants cannot change too much without rendering the universe lifeless. But how much tuning can we have before we should get suspicious? As Fred Adams has shown, it is actually harder to tune a radio than a universe, and we may not live in the most life-friendly of all worlds. So could fine-tuning just be an illusion? A fundamental theory of nature may one day settle these questions, telling us what values we should expect the constants to have in the first place. Or maybe a space telescope will reveal that the constants are not constant at all, meaning there's nothing too special about the specific values that we measure at a certain time or place. But for now, we have to accept the possibility that our entire universe is just a plaything for an alien advanced civilization, looking at us through a wormhole or in a computer simulation. Maybe they're laughing at us for trying to figure it all out. For now, Many physicists are happy to just rely on the idea that our universe is ultimately just one of many in an infinite multiverse. If so, we would expect some of these universes to be life-friendly. But how seriously should we take this notion? Is there actually any evidence to back up the idea that there are multiple universes? Is it even science?
I think it's fine for entertainment. I think it's very inspirational. People just love talking about it. They live out their fantasies. What could happen if I could live my life in some other way, in some other universe? I'm not a big fan of this being used in science as a mode of investigation of the natural laws of nature.
That's Sabine Hossenfelder. She does not believe in the multiverse theory. And we'll hear more from her and others next time.
This podcast was created and presented by me, Miriam Frankel, and produced by Hannah Fisher. The executive producers are Joe Editunji and Gemma Ware, and the advisory editor is Zia Morali. The sound design is by Eloise Stevens, and music is by Nita Sarl. Great Mysteries of Physics is a podcast from The Conversation UK, with funding from FQXI.